Welcome to the final video in our first video series. We're going to begin with a discussion of ionization of water and definitions of pH. However, we should point out that the main way that we're going to consider ionization is of side chains of amino acids and less so of water. What we will find, of course, is that the pH of a solution is going to determine the ionization state of a side chain, and that's going to be of very great importance to our understanding of the behavior of biological molecules. This should be pretty trivial review for you, but let's run through it anyway. Water, of course, ionizes, and the formal way to write this down is to say that two water molecules dissociate to form one hydronium ion, H3O+, and one hydroxide ion, OH-. Now, we write it this way because we don't consider protons to be dissociated from a water molecule ever. Instead, they're always associated in a form of a hydronium ion, H3O+. However, for convenience sake, we tend to write it this way. One molecule of water dissociates to form a hydronium ion and a hydroxide ion. This, of course, is an equilibrium for which we can write an equilibrium constant. Products of the dissociation over the reactants of the dissociation. And because water does ionize, but it only does so to a very small extent, that is, at any given time there is very little dissociated into ions, we can disregard the water itself because that's always going to be at something approximating about 55 molar. Instead, we write the Kw, which again eliminates the water from the equation so that we're only considering the concentration of the dissociated ions. In water at 25 degrees, the Kw is something like 1 × 10⁻14th molar squared. Now, of course, we know that the concentrations of hydronium ion and hydroxide ion must be equivalent. So if we take the square root of this, we get the concentration of the hydronium ion or the hydroxide ion in isolation. That's going to be 1 × 10⁻⁷ and you can get the sense of where we're going with this. Take the log of that number, you get something like 7, right? Physiological pH. So here, to take a look at this, we say that those ion concentrations are equal. Individually, they're 1 × 10⁻⁷. Here's our formal definition of pH, equals the negative log of the hydronium ion concentration, 7. Now, we can see what happens to the pH as the ion concentration changes. Here on the left we have a logarithmic scale of concentration, and we see that at very high concentration of hydronium ion we have a low pH. pH gets higher as hydronium ion gets lower, right? And conversely, hydroxide ion concentration increases in terms of water. Now here is our Bronsted-Lowry definitions of acids and bases. We might use others over the course of the semester, but this is the easiest one for discussing what's happening to the ionization state of weak acids and amino acid side chains. We just state that acids donate proteins, they dissociate and increase the hydronium ion concentration, whereas bases accept protons and they dissociate, increasing the hydronium ion concentration. Now, I might also say that most of the time we're going to see that when acids dissociate, they become negatively charged, right? So when a carboxylic acid loses its proton and becomes a carboxylate ion, it's a negatively charged ion. Likewise, bases tend to accept protons, becoming positively charged. We've already seen how imidazole can accept a proton and become positively charged with a pKa of around 6. Alright, now strong acids dissociate completely. We're not really concerned with strong acids in this course like hydrochloric acid, which do dissociate completely. Instead, we discuss ions or acids and bases that only dissociate weakly. Partially dissociate. This is an equation for the behavior of acetic acid. So the weak acid is acetic acid here. You see that it's protonated. It can dissociate to form hydronium ion and its conjugate base, the acetate ion. We can write the Ka for this dissociation in the following way. Again, products over reactants. And we can define something called a pKa, which places this number, which is actually quite a small number, in much more manageable terms. Let's think about whether given this value, whether the molecule, whether the acetic acid molecule is actually more dissociated or less dissociated. So I'll let you chew on that yourselves. What does this mean? What's happening in the numerator and the denominator for us to get this very small number? And what does that mean for the dissociation state of most of the acetic acid? We'll discuss that in class. Chew on it now. It's not a very complicated problem. In any case, this number is small, so we recast our equilibrium constant in terms of its negative log, and that is 4.76. So you can see that 4.76 is a little bit more manageable number than 0.00018 or 1.8 times 10 to the minus 5. In any case, this is how we describe the dissociation state of the weak acid. Now, here's the Henderson-Hasselbalch equation, and it's going to let us do something very important. Let's skip to the bottom for a second before we go ahead and do our little derivation. We see that what we can do is describe the pH. And we describe the pH of a solution in terms of the pKa, right? And that's going to be unique for a given a weak acid or weak base. And we also describe it in terms of the log of the ratio of these concentrations. How much acid is present, how much conjugate base is present, how much weak acid is present. So again, taking acetic acid as an example, right, the weak acid has a proton to donate, and the proton acceptor is the conjugate base. Oops, hello, come back. Right, there's the conjugate base. Right, so again, pH can be expressed in terms of the pKa of the weak acid and the log of the ratio of the concentrations of the conjugate base and weak acid. All right, so here we say, here's our definition, log Ka equals log of this ratio, of course, and we can use some of our rules of logarithms to just start to split that out so that we can now define the solution pH in terms of those solution components. So splitting out the log of the hydronium ion concentration, that's a very useful thing to do. Why? Because we already have a definition of the log of the hydronium ion concentration. That's related to pH. So now we say that the log of the Ka equals the log of the hydronium ion concentration plus the log of, there's our two buffer components or solution components, conjugate base and weak acid. And now we can just rearrange so that, again, we can express things in terms of something we already have a definition for, that is the pH. So we move our log of the hydronium ion concentration over, we bring the log of the Ka over, and of course the negative log of the Ka is what? The pKa. So we see that we can very simply derive the Henderson-Hasselbalch equation in terms of everything that we already know, which is just the Ka of the weak acid. This is very powerful, right, because it allows us to decide what ratio of solution components we need to use in order to achieve a particular pH. So let me emphasize that there are two ways that we can use and think about this equation. Way number one is, let's say that we want to make a buffer, and that's mostly what we're going to discuss in this lecture. How do we make a buffer? Well, we want to have a buffer that's at a defined pH. Remember that in any kind of experimental situation, we want to define the solution pH. So we decide what pH we're going to use, we use the weak acid that's relevant, and I'll show you a list of those in a moment, and then we figure out what the ratio of weak acid and conjugate base should be. There's a second way that we'll wind up using this equation as well, and again that has to do with deciding what the ionization state of a weak acid is under a particular pH condition. But let's stick with buffers for now. You've seen this already. I've added one detail to this figure, that is showing you where the buffer works. Now, most of us probably already know what a buffer is at this point, but let me just state that a buffer is a weak acid or a weak base that allows us to control the pH of our experimental conditions. So we see already that we've made some definitions, right? We say that the pKa is the pH at which the weak acid and conjugate base concentrations are equivalent, right? So you can also think of that as being halfway, right? There's 0.5, but it's halfway titrated, right? So we're halfway through the titration curve. Now, in terms of buffering, a rule of thumb is to say that the pH is going to be well buffered plus or minus 1 pH unit from the pKa of the weak acid or weak base. So buffering capacity is maximized at the pKa. So we'll take that into consideration when deciding what kind of buffer we want to make. And remembering, I might as well say that when we're 100% titrated for a weak acid, we've completely titrated that to its conjugate base by adding one molar equivalent of base. So how would we decide what buffer to use? Well, I think I stole this from the Sigma Aldrich website, and it shows you a range of pHs. And you should realize that physiological pH is 7, so frequently we're going to be working somewhere around pH 7 in biochemical experiments. This is a list of organic buffers that have been created over the last several decades that allow us to control pH over a fairly fine range. So you have a variety of buffers that you can choose from to control your pH. And this is just a nice table for you to refer to. I'm not going to define all of these, and I certainly don't want you to remember all of these, but I want you to be aware of them and sort of be familiar with them as you go through your careers as biochemists. So you'll see here a useful pH range for these, and that's depicted graphically here. You can see too that many of these have multiple pKa's, that is, they're polyprotic acids, just like we've discussed for phosphate. I'll come back to these in a moment. Some that you might be familiar with already would be tris. Some of you might have worked with pipes, mops. Heaps is another one. Where's heaps? There's heaps, right? There's a variety of others that you will have worked with or you will be working with over the course of your careers. However, let me point out that there are a few buffers that are very handy to use in the laboratory. Phosphate is a buffer that's used very frequently, can be used with a variety of counterions. Sodium and potassium are the most common, and you see that it has a pKa that's in our useful range. Acetate and formate are also very useful buffers, and let me just give you a good reason for that. You can see that their pKa's are outside of the physiological range. However, we still use them frequently, and that's because we can manipulate the pH of a solution just by adding the acid and its conjugate base. So we have acetic acid is a commonly available acid, and there's a variety of salt bases that are readily available. Sodium acetate, again, potassium acetate, and the like. Similarly, for formate, it's easy to come by formic acid as well as its conjugate bases. So those are handy because for example, if we want to avoid changing the ionic strength of the solution, say by titrating our buffer with acid or base, say hydrochloric acid or sodium hydroxide, both of those are going to increase chloride or sodium concentrations. So instead we can work with these buffers and only have as solution components the weak acid and its conjugate base, and we can dial in our pH exactly. So there's some useful buffers. These are handy experimental buffers as well. But let's use what we've learned about the Henderson-Hasselbalch equation to make a buffer. So the next couple of slides are going to describe how you might go about deciding to make a buffer solution. And what I've skipped in this part, in this lecture, is the final aspect of this, which is straight up general chemistry dimensional analysis. We'll review it a little bit in class, but really this should be something that you should be very familiar with already as senior biology and chemistry majors. In any case, let's go back to acetic acid. Here it is again, dissociation of acetic acid. Here's its pKa. Right? One way to make a buffer is to go back to our Henderson-Hasselbalch equation and say, all right, well, let's choose some ratios of these two without considering actual molar quantities at this point. Let's choose a couple of ratios and see what happens to our pH. So first we'll say, all right, let's use twice as much conjugate base as weak acid, twice as much, let's say twice as much sodium acetate as acetic acid, plug in our pKa, out comes our number. And you can always check yourself this way by understanding where you are with respect to the titration curve. More conjugate base, that means the pH is going to be above the pKa. Remember, pKa is the concentration of conjugate, it's the pH where the concentration of acid and base are equivalent. We can take the converse example here, right? Now choosing to use half as much conjugate base as weak acid, and we see that the pH drops below the pKa. That's a good rule of thumb. More weak acid, pH drops below the pKa again. So you can always refer back to your titration curve to make sense of this. pKa, concentrations are equivalent. Add more acid, we're below the pH. Add more base, add more acid, we're below the pKa. Add more base, we're above the pKa. However, you might want to dial your pH in precisely, so you might want to do a little calculation and determine what the proper ratio of weak acid to conjugate base is. And here's a simple way to do that. There are other ways, but we'll focus on this particular way. So, determine the proportion of conjugate base to acid at a given pH. So now we're going to plug in our desired pH. Say again we're using acetic acid. So here's the pKa. We want to work at pH 5. Now the question becomes, well, what's the proper ratio? Very simple to figure out. Here we just rearrange, subtract our pKa from our desired pH, and raise that to the proper exponent, and we come out with our ratio. Okay, so that's something that I want you to practice, and I've given you homework assignment to practice there. I know we're not all the way done. Now all we know is the ratio, but now let's solve. Let's solve for the concentration, right, of conjugate base. Well, this expression allows us to say that the concentration of conjugate base should be 1.74 times that of the weak acid. That should again make sense with respect to what I just told you on this slide. More conjugate base, pH above pKa. We're shooting for a pH of 5, that's above our pKa, so we expect to have more conjugate base than weak acid. For some reason, this always trips people up, but what I really want you to keep clear sense of is what do we mean when we're solving for A minus here. What we're doing is solving for the concentration of conjugate base, and we're expressing that as basically in relation to the weak acid concentration. So another way to say it is to think that for every mole of acid we must use 1.73 moles of its salt, the conjugate base. You can set this up to get it at a precise percentage of molar percentage if you like, and you can do that this way. You say that for every 1 mole of acetic acid we have 2.7, oh, that should be 2.73, sorry, 2.73 moles total. So that's 1 mole of acetic acid, 1.73 moles of conjugate base. That's for a total of 2.74, right? The fraction is the part over the whole. That gives us a 36.5%. We can do the same calculation for the conjugate base. We say for every 1.7 moles of conjugate base, there's a total of 2.7 moles of acid and base, and that gives us, you can also subtract 1 from 1 and you get the same thing, 0.64 or 64% acetate. Again, let me emphasize that should make perfect sense, right? We expect to have more conjugate base than weak acid because our target is above the pKa. Okay, now again, what I've omitted from this calculation is the actual dimensional analysis that's going to let you calculate how much of each of these you're going to use. Right now, you're just still expressing it as a percentage or some proportion. If whatever the number of moles you're going to use, 64% of those moles are going to be acetate. Whatever number of moles you're going to use total, 36.5% of those are going to be acetic acid. That's a calculation that I'll expect you to be familiar with when we come to class next Tuesday or next Wednesday after Labor Day. Okay, let me bring it back home. So we've been discussing the ionization of weak acids in terms of buffers, but I also said we like to think of ionization state in terms of biochemical activity, and this is an example that we'll discuss ad infinitum this semester. This is a serine protease. It's a ribbon diagram of a serine protease, and what I've done is highlight, and again, we haven't discussed these protein structures very much, but let me just say that we'll elide the complexities of this structure and then focus on the amino acid side chains that I've drawn in red for you. This is a protease. It cleaves polypeptides, it cleaves peptide bonds. How does it do it? Well, it depends very intimately on the ionization state of amino acid side chains and the malleability of that ionization. So here, this active site that I've highlighted in red is often referred to as a catalytic triad. And that is because there are 3 amino acids that act together in concert, culminating with effectively the ionization of this hydroxyl group. Now, what I've already told you in this series of lectures is that a hydroxyl at pH 7 ain't likely to ionize. but we need that guy to act as a nucleophile. How do we make it do that? Well, we begin with an aspartic acid. Now, you don't know all your amino acid side chains yet, but let's just say that this guy is a carboxylic acid, and he happens to be ionized at pH 7. He's placed in close proximity to this imidazole, which, happily, is a nice base that can accept a proton. But what it can do right now is engage in a hydrogen bond with the carboxylic acid, and in fact, that hydrogen bond could result in the abstraction of that proton. Certainly it'll engage in a strong hydrogen bond. What that does is make the imidazole even a better base, and now this lone pair on this nitrogen is going to interact with the hydroxyl in a strong hydrogen bond. Now you could take it all the way to the abstraction of that proton by the nitrogen base, and then the imidazole becomes protonated and charged, which it happily does around a physiological pH. But in any case, this strong interaction of the base with that hydroxyl proton activates the serine hydroxyl to become a strong nucleophile so that it can attack the peptide bond. So again, the point being that understanding the ionization states of these amino acids and the malleability of those ionization states is central to understanding biochemical mechanism. That brings us to the end of this first series of videos. We'll move on to the amino acids in the next series of videos, but before you do that, I hope that you take time to participate in the self-test. You'll be able to take that self-test as many times as you like before the actual quiz for this section. Enjoy! See you next time.